Hello everyone, I am T. Likith Kumar, a first year BTech student from Data Science Department at Gokaraju Rangaraju College. I am glad to have this opportunity to demonstrate an important experiment from our Applied Physics Lab course using the Virtual Lab platform. As part of our first year curriculum, the Applied Physics Lab consists of 10 carefully designed experiments that introduce us to the fundamental concepts of modern physics and their practical applications. These experiments covers a wide range of topics from optics and semiconductors to electromagnetism and energy devices, giving us a solid foundation in experimental physics. Today, I will be demonstrating one such experiment, that is the energy gap of a semiconductor using p-n junction diode. Aim: to determine the energy gap of semiconductor using a p-n junction diode. Apparatus: microboard kit consists of germanium semiconductor diode and microammeter and regulated DC power supply, thermometer, oven and copper vessel, bakelite lid and connecting wires. C. Aim: to determine the energy band gap of a semiconductor using p-n junction diode. This is our virtual lab. See, in this aim: to determine the energy gap of a semiconductor using p-n junction diode. Next theory. See, what is the theory behind the energy gap of a semiconductor? We know in semiconductor there are two bands. One is valence band and another one is conduction band. This gap is called energy gap. This gap is called energy gap. This band is called band gap. The distance from valence band to conduction band is called band gap. Based on band gap, materials are classified into three types: metals, semiconductors, and insulators. See, in metals, valence band and conduction band overlap with each other. There is no band gap. So metals have high conductivity. In semiconductors, see, the distance between valence band and conduction band is very less. So semiconductors have less conductivity when compared to metals. In insulators, the band gap is very high. So insulators have no conduction property. Next, stimulation. Start. Thermometer. This is our thermometer. Voltmeter. See, this is our voltmeter. Heater. This is our heater. Diode. This is p-n junction diode. Ammeter. This is our microammeter. DC power supply. This is DC power supply. Next, select the element. We are doing experiment with germanium. So select germanium semiconductor. Select the least count. Select least count as 5. Means temperature difference is 5. Then set up the voltage. Set voltage as 2 volt. And turn on the heater. Again turn off the heater. Now note down the readings. At 80 degrees centigrade, our saturation current is 207.75 microamperes. Again decrease the temperature. At 75 degrees centigrade, our ammeter reads 187.46 microamperes. So at 75 degrees, saturation current is 187.46. Again decrease the temperature, 70. At 70 degrees, our saturation current is 171.47 microamperes. Again decrease the temperature, 65. At 65 degrees centigrade, our saturation current is 157.41 microamperes. Next, our observation values are correct. See, this is our observation table. Temperature, saturation current, temperature in Kelvin, 1 by T, log IS to the base 10. See, here temperature is in centigrades. IS is saturation current. It is in microamperes. Because given semiconductor, we are calculating energy gap of a semiconductor using p-n junction diode. Here p-n junction diode is in reverse bias. In reverse bias, we will get microampere current, means small amount of current. This is our saturation current. See, temperature is in kelvins. We will get kelvins when we are adding 273 to centigrades. 80 plus 273 is equals to 353. 1 by T and log Is to the base 10. Next, see these are our readings. At 59 degrees centigrade, we got 144.01. See, these are our observation values. Next, we're going to plot the graph. See, this red line indicates best fit, means this theoretical. This blue line is our experimental. Now we are calculating slope. To calculate slope, we want any 2 points. What is the formula of slope? y2 minus y1 by x2 minus x1. Suppose select this point and enter x1 value and x2 value, y1 value and y2 value. Select any 2 points and enter here x1 value and x2 value and y1 value and y2 value. See, x1 value is 2.865 and x2 value is 2.833. y1 2.278 and y2 2.303. I calculated slope by using formula y2 minus y1 by x2 minus x1. I got slope as 0.78. Check. Yeah, our slope value is correct. Now calculate the energy gap of germanium by using energy gap formula 0.5036 by slope. What we got slope? 0.78. 0.5036 divided by slope means 0.5036 divided by 0.78. What we will get? 0.6456. Verify. Yeah, calculated band gap is correct. The experimental value of energy band gap is of germanium is 0.639 volt. See, what they're asking one question. Standard energy band gap of germanium is given as 0.7 volt. Is calculated band gap greater than standard band gap? What we got? Calculated band gap. See, this is energy band gap. This experimental value, what we got? 0.639. What experimental? 0.639. Calculated also 0.639. Standard C, 0.7. C is calculated greater than standard? No. Submit. Correct answer. Next. Our calculated band gap is correct. See, finally we calculated the band gap of a given semiconductor by using PN junction diode. What we got? 0.639 volt.